Hello, sir. My name is Nandu Thanneeru. Today I am going to explain about the topic simulation of a low bypass turbofan engine with an injector nozzle using NPSS. Introduction. Engine configuration. Start by defining the overall configuration of your engine, including the number and type of components such as compressors, turbines, and injector nozzle. Specify the geometric and operational parameters for each component. Component modeling. Create component models for each part of the engine using the appropriate NPSS libraries. NPSS provides various libraries that represent different types of components such as compressors, turbines, combustors, and nozzles. You, you will need to select the appropriate models and configure them based on the characteristics of your engine. Turbofan with an injector nozzle using NPSS. Find connections. Establish connections between the components to represent the flow of air and gases through the engine. Specify the flow rates and conditions at each connection point, including temperatures, pressures, and fuel to air ratios. Set boundary conditions. Define the inlet and outlet conditions for your engine. This includes specifying the atmospheric conditions in the inlet, such as temperature and pressure, and the desired nozzle exit conditions. Second one, configure solver settings. Set up the solver settings for the simulation. Third one, this includes selecting the appropriate solver algorithm, specifying convergence criteria, and defining time step sizes for transient simulations. Run the simulation. Execute the simulation using NPSS. The software will solve the governing equations for each component and iterate until a converged solution is achieved. The simulation will generate results for various parameters such as thrust, fuel consumption, and component performance. Analyze the results. Once the simulation is complete, analyze the result to evaluate the performance of your engine. Examine parameters such as thrust, fuel efficiency, temperature, pressures, and component characteristics to assess the behavior of the low bypass turbofan engine with the injector nozzle. Turbofan engine of low bypass. Turbofan engine that derives most of its thrust from the jet engine or flux is referred to as low bypass engine, whereas an engine that derives most of its thrust from the fan is referred to as a high bypass engine. Variation of the bypass nozzle exit area levels. Optimization of the turbofan engine operating cycle over a wider range of operational conditions resulting in improved thrust and fuel consumption. Case of low bypass turbofan, the response of the low bypass turbofans to throttle adjustments is faster compared to the high bypass turbofans. The inertia is less and less air mass is involved for increasing the velocity. This is during combat and thrust requirements change rapidly. Typical low bypass ratio engines have one or two stages of blades in turbine which are used to extract power to drive the compressors and the fan. High bypass turbofan engines have multiple turbine stages which work to extract more power to drive the large diameter fans. Range of low bypass turbofan engine, low bypass turbofan and turbojets. In the next higher nature of aircraft flight speed, the low supersonic range from Mach numbers above 1 up to 3. One finds the application of the simple turbojet with no bypass stream and low bypass turbofan engine with the bypass ratio up to 2. The turbofan engine, low pressure fan, high pressure compressor, combustion chamber, afterburner, jet, variable exhaust nozzle, mixer, fan turbine, flow turbine. Possibility of extracting large amounts of electrical power from turbofan engines is becoming increasingly desirable from an aircraft perspective. The power consumption of a further fighter aircraft is accepted to must much higher than today's fighter aircraft. Previous work in this area has concentrated on the study of power extraction for high bypass ratio engines. This motivates the through investigation of the potential and limitations with regards to performance of a low bypass ratio mixed flow turbine engine. A low bypass ratio mixed flow turbofan engine was modeled. The key parts of a fighter mission were selected. Possibility of extracting large amounts of electrical power from turbo engines is becoming increasingly desirable from an aircraft perspective. A further fighter aircraft is expected to be much higher than today's fighter aircraft. Previous work in this area has concentrated on the study of power extraction for high bypass ratio engines. This motivates a true investigation of the potential and the limitations with the performance of a low bypass ratio mixed flow turbofan engine. A low ratio mixed flow turbine engine was modeled. A key parts of fighter mission was generated. Range of low bypass turbofan, low bypass turbofans and turbojets. In the next higher of aircraft flight speed, the low supersonic range from Mach numbers above 1 to 2 or more. One fine application of simple turbojet with no bypass engine and the low bypass turbofan engine with a ratio of 2. Advantages of low bypass turbofan. The response of the low bypass turbofans to vertical adjustment is faster compared to the high bypass turbofans. The inertia is less and less air mass is involved for increasing the velocity. This is important during combat. Requirements change rapidly. Typical low bypass ratio engines have one or two stages of blades in the turbine which are used to extract power to drive the compressor and the fan. High bypass turbofan engines have multiple turbine stages which work to extract more power to drive the large diameter fans. Conclusion. It's important to note that NPSS is a commercial software package and you would need a valid license to use it for engine simulations. Additionally, detailed knowledge of the engine components, thermodynamics, and fluid mechanics is necessary to properly configure and interpret the results of the simulation. Thank you, sir.